We've been juggling with the number of clusters for too long. Isn't there a criterion for setting the proper number of clusters? Luckily for us, there is. Probably the most widely adopted criterion is the so-called elbow method. What's the rationale behind it? Well, remember that clustering was about minimizing the distance between points in a cluster and maximizing the distance between clusters? It turns out that for k-means, these two occur simultaneously. If we minimize the distance between points in a cluster, we are automatically maximizing the distance between clusters. One less thing to worry about. Now, the distance between points in a cluster sounds clumsy, doesn't it? That distance is measured in sum of squares, and the academic term is within cluster sum of squares, or WCSS. Not much better, but at least the abbreviation is nice. Okay. Similar to SST, SSR, and SSE from regressions, WCSS is a measure developed within the ANOVA framework. If we minimize WCSS, we have reached the perfect clustering solution. Here's the problem. If we have the same 6 countries, and each one of them is a different cluster, so a total of 6 clusters, then WCSS is 0. That's because there is just one point in each cluster, and we can't have a within-cluster sum of squares. Furthermore, the clusters are as far as they can possibly be. Imagine this with 1 million observations. A 1 million cluster solution is definitely of no use. Similarly, if all observations are in the same cluster, the solution is useless and WCSS is at its maximum. There must be some middle ground. Applying some common sense, we easily reach the conclusion that we don't really want WCSS to be minimized. Instead, we want it to be as low as possible while we can still have a small number of clusters, so we can interpret them. All right. If we plot WCSS against the number of clusters, we get this pretty graph. It looks like an elbow, hence the name. The point is that the within-cluster sum of squares is a monotonously decreasing function, which is lower for a bigger number of clusters. Here's the big revelation. In the beginning, WCSS is declining extremely fast. At some point, it reaches the elbow. Afterwards, we are not reaching a much better solution in terms of WCSS by increasing the number of clusters. For our case, we say that the optimal number of clusters is 3, as this is the elbow. That's the biggest number of clusters for which we are still getting a significant decrease in WCSS. Hereafter, there is almost no improvement. Cool. How can we put that to use? We need 2 pieces of information: the number of clusters, k, and the WCSS for a specific number of clusters. K is set by us at the beginning of the process, while there is an sklearn method that gives us the WCSS. For instance, to get the WCSS for our last example, we just write k-means dot inertia underscore. To plot the elbow, we actually need to solve the problem with 1, 2, 3, and so on clusters and calculate WCSS for each of them. Let's do that with a loop. First, I'll declare an empty list called WCSS. For I in range 1 to 7, as we have a total of 6 observations, colons. K-means equals K-means with capital K and M of I. Next, I want to fit the input data x using k-means, so k-means dot fit x. Then, we will calculate the WCSS for the iteration using the inertia method. Let WCSS underscore iter be equal to k-means dot inertia. Finally, we will add the WCSS for the iteration to the WCSS list. A handy method to do that is append. If you are not familiar with it, just pick the list, dot, append, and in brackets you can include the value you'd like to append to the list. So, WCSS dot append brackets WCSS iter. Cool, let's run the code. WCSS should be a list which contains the within cluster sum of squares for one cluster 2 clusters, and so on until 6. As you can see, the sequence is decreasing with very big leaps in the first 2 steps and much smaller ones later on. Finally, when each point is a separate cluster, we have a WCSS equal to 0. Let's plot that. We have WCSS, so let's declare a variable called number clusters, which is also a list from 1 to 6. Number clusters equals range 1, 7. Cool. Then, using some conventional plotting code, we get the graph. Finally, we will use the elbow method to decide the optimal number of clusters. There are 2 points which can be the elbow, this one and that one. A 3-cluster solution is definitely the better one, as after it there is not much to gain. A 2-cluster solution in this case would be suboptimal, as the leap from 2 to 3 is very big in terms of WCSS. Okay, let's wrap it up here and we will practice this new knowledge on other datasets in our next lessons. Thanks for watching.